It's really to present the challenge at the multidisciplinary level and the multi-scale level. So really present the complex case in the real world of our mine site and the extreme, the whole range of domain. How do we deal with it? It's really to give the message so academics and industry practitioners should collaborate in a multidisciplinary fashion. I'm and together with Jason, we're chairing the session. Unfortunately, we have a very senior person from Rio Tinto, but he got called away to the middle of the nowhere of Quebec, so I can't find him. Yeah, David Parry is very busy because there's a lot of mine closure issues coming up. So I choose this topic, may not be that comprehensive, but really just to see the whole range of issues on a mine site and how do we deal with it, and specifically point out the toxic mine waste, which is the really difficult part. At the same, I do have to appreciate a lot of the past and present group members, and I utilize some of the cases, and I haven't got PHP funding me, so they haven't got that logo. That's the next task to work on. What I'm going to cover is the basically the 5 points. Just I think a lot of you from the mine side or work on mine side, you understand that I took the opportunity to show a whole range of typical mine site, a different domain for people who haven't been to the mine site very much. So what's the complexity? And secondly is, what is the characteristic problems, challenges, especially try to pose the message of multidisciplinary and multi-scale resolution. I think academics are very good at pot trial and test tubes, but we need to take that concept and enlarge it to encompass, to embrace the complexity and challenge of the real world. And I call it last frontier of mine rehabilitation toxic mine waste because it is most difficult and most expensive. In many sites, just the tailings part can cost more than 50% the total closure cost. And basically introduce some concepts about total system approach. And I used a real world case in Wahi, New Zealand. So if you do it properly, you can be successful. It's a gold mine. I like that mine site very much. I have been there. Yeah. So this is the photos I got together in the past. So this is sand mine. So a lot of the biological disturbance and some of the fertility disturbance. So the condition of this Stradbroke sand mine has to restore to the same physical and geographical design, so the slope, etc. This site highlighted again topsoil. Topsoil been brought up very, very frequently, and the same here. They store topsoil. There's a trial somewhere here. This side they use the old stored topsoil, and then this side they use freshly 6 months topsoil. And then after bushfire trial, the seeds all come back, even more diversity. But the old topsoil, many species disappeared. So the topsoil concept was brought up in this site. That's a coal mine, okay? The coal mine, this is Tyrone coal mine. They're doing a lot of good rehabilitation trial. The problem is, again, it's water, landscape design, erosion issues, and sodic spoils problem is typical associated with coal mine. So when you're doing the contour and layering, if you use wrong material at the wrong order, you're inviting for trouble. So it's a different issue here. That's a photo I took the Whaleback iron ore mine. I don't know how to do this. It's so scarred. And lack of soil, lack of water. So this, again, it's a physical, complete loss of the soil system and geological support. Okay? I think, I don't know, I'll have to borrow Jason and Todd's experience probably not much toxicity in this kind of environment. And this is the Leyshon gold mine. This is a typical cover design, and for physical and landscape design for physical beauty. But this acid water, pyritic material buried at the bottom, it's a geological fault. So when the water rises to a certain level, if you're not careful, they follow the fault line going to the river, and it happened once. So they have to buy up all the farm along the river. And so they set up the sewage ponds to contain arsenic. This is typical problem of when they design this cover, they do not pay attention to geochemical stability. They're more paying attention to physical stability. When you're dealing with pyritic waste rock, you have to be very careful. This mine life, operating life, is 16 years, but the maintenance and management is more than 20 years now. All the money earned is given back. So you can see they have to go back and redesign all the water, diverge the water. You have this vegetation disappearing because acidification, etc. And you can see the acid mine drainage still happening. That's a red mud dam from the Google Earth. Okay, how do we deal with this? pH 12, 13. Mount Isa mine, okay, you have silver pit, you have refinery, you have plants, buildings. Look at this footprint of the mining bits. You look at the tailings bits. So this is, if you allow the other margins, contaminate land altogether, probably about 15, one more zero too much. So it's 1,500 hectares. So that's a lot. And again, the same thing, we don't have any topsoil. And again, if you don't have stable ecosystem to rehabilitate this progressively, you lived in the environment too much, you have to have very expensive care and maintenance to make sure this kind of disaster doesn't happen. Okay? I'm not saying this disaster happened because no ecological rehabilitation, but if you leave it for long enough, extreme weather events, then this risk could be higher. This is because the waterhead pushing the dam open. Again, this is, you all know this, the iron ore tailings, okay? So really, you can summarize the domain into more about disturb the road, the factory, the building. There's about degraded, damaged land, so storage places, production storage places. But the most difficult is that last bit, the complete loss of real rigorous and supporting geology, and especially occupied by contaminated mine waste. And a lot of the metal mine, apart from iron ore, the economic liability is very high for this part. And it's a long term. Okay? So, as you're saying, you need lots of stuff to deal with this. And you need to start from very different places. Soil science alone doesn't going to solve the problem. Plant science alone doesn't solve the problem. So we need to do multidisciplinary. We need collaboration among different disciplines who can share the common dream of solving problems. That's important. So we'll have to have a common goal. And it's a multi-dimensional resolution. We are very good at this level, substrate level. And how can we expand it into more landform level? How can we put the landform units so we can work out the landscape system? So we need people addressing the micro, intermediate and macro landscape level, if we're really going to deliver the industry solution. Okay. So that's what we've been saying. It is the ecological engineering process of the total ecosystem, which you should have the stable and sustainable biotic structure. This component, we are very good at it because we get the bulldozer, we put rock, we put soil, we put plants, very good at it. What difficult is, how can we let them evolve so they are interlinked with functional ecological processes. Like I said, the water flow in the right way, the nutrient cycling going on the right way, the seeds recruitment, the species diversity evolved the right way. And end of the day, we have to be able to deliver the ecosystem services. For example, if that's the criterion target is for regulating local climatic change, then you have to fit that requirement. If it's for local wildlife, you have to fit that ecosystem services. So this has to be substantiated, not just the principle, it has to be substantiated based on the site-specific condition and requirement. And very importantly for metal mine, especially base metal mine, is no polluting. Okay? So the food come out of the plant community should be clean, and the dust come out of the plant, footprint shouldn't contain contaminants, and also the water. As I was saying, this is a very beautiful place. It's a gold mine, was an abandoned mine, Golden Cross, but when Newcrest took over the current mine, they took on the liability and put in some money in. They follow the ecological engineering. They probably did not realize that, but they really follow that principle very well. They utilize water because they got lots of water. So they utilize water to flush the waste and the underground tunnels and pump the dirty water back to the tailings pond and then treat the water there. So now the whole site, they are only doing physical stability monitoring with the radar. And the whole site is very, very, very nice. Then they put a $50 million as a community service trust fund for the local shire to do long-term maintenance. It's a picnic place. If you have chance, go there. I really like that place because you got the typical metal mining places. That's a pit, and then they went to underground. That's the tailings pond in the past. And at the same, the waste, mining waste is really problematic. And when you sit on about 1,500 hectare tailings dam at Mount Isa mine, which covered with all the salt crust, you don't know what to do. Okay, it is without seeing it, you won't be taking in, and it's a volume so much. And last 2 weeks ago, we had a alumina conference in Glasgow, and there's about world 50% bauxite residue in China. So what is it going to do with it? Maybe they can export those back to Australia. And the challenge in Dorming is the cost very high. The trouble is very uncertain long-term environmental ecological sustainability. That's what I think many companies start to realize. We need to do some research rather than just cover. But when you have the mountains like New Zealand, you can do it. You probably get a permission and blast the mountain cap on it. But we don't have many mountains in Australia. We have, I call the pit as negative mountain. And some of you probably know this tailings is really grinding everything up to the last minute, put some chemicals, get the useful stuff, not used stuff, pump in, and see you tomorrow. And in general sense, tailings physically very fine, very fine texture, and mineralogical wise, they can go very extreme. Iron ore tailings is quite benign. Okay, so lack of secondary mineral of silica and iron. But pyritic tailings are energy too high. If you give a little bit of moisture, not necessarily oxygen. I think a lot of people get confused. Acid mine drainage is caused by exposure to oxygen. No, it's exposure by moisture. And the microbes oxidizing sulfide and iron, they do not need oxygen. They need carbon dioxide to build there. So even you cover it, does not allow the oxygen to penetrate through. They still work on it, as long as it's got moisture. Okay, that's very high, why very hard to control acid mine drainage in a big scale. So in our iron ore tailings, we try to elevate the energy level, but in the pyritic tailings, we try to lower the energy level by utilizing microbial and biogenic factor. Because really, I think I try to take the opportunity to also correct some concepts. I think traditionally people always start with too high level, equate tailings or mine waste as soil. You can, I think, even you go back to the literature, so many people always mention the nutrients, so many of them, acidity, alkalinity, nutrients. Don't start with fertilizer, you waste your money when you're dealing with tailings. Because they are not soil, they're nothing like soil, because they're just dominated by polymineral metallic waste. Okay? And this is what the tailings look like cheesecake. So I have to push in is tailings are not soil. It's engineered polymineral waste of geological origin without favorable chemical, geochemical, physical, and biological properties. That's what tailings is about. Okay? And tailings rehabilitation are not soil or land remediation. So don't use remediation. Remediation is when the tailings get to a certain degree of improvement where it have primary physical chemical properties can support biological activity, then the remediation tactics can start kicking in. Okay? I often take the analogy when the human's organ all failed, you need organ transplant, not the vitamins. It's not useful. And rehabilitation is not restoration, not revegetation. It's destroyed. We cannot pretend we can restore to pre-disturbed land. You like it or not. The same. If you have a bionic heart or triple transplanted heart, okay, you can recover to certain human function, but I cannot expect you to be exactly the same as before the heart went wrong. It may take several thousand years, but which I don't know. Anyway, too far away. Okay, so with such a big volume and such a big area, this conventional carver technology, in theory, works, but in practice, it's very expensive and very hard to implement because we don't have enough swelling clay in Australia. Okay, so we need to have some different tactics. That's the calculation which I showed in last conferences. This is just for 3 types of mine waste in operating mine. That's not including manganese, doesn't include other iron ore tailings, doesn't include tin or abandoned mine. This is just operating mine. That's the cost we're thinking about. If you use the cover design, or the government asks you to do 2-meter cover design. Okay? So we're really, this is, end of the day, whatever you do, you're aiming to achieve this. Whatever you do. Okay, you can interpret, if you can substantiate, interpret. And in the stability perspective, this is very important when you're dealing with polluting mine waste. I suppose in the iron ore country, the physical stability, especially erosion, wind erosion, is a big problem. I quite often ask the tailings stand to build maybe a car racing ground or a Hollywood movie facility for space war or some kind of. And it is a holistic approach, and we need to address all these hydrological cycles, biochemical cycles, and capable of I just bring this back to our mind. Okay, when we're going to do projects for industry, we need to put this first, and then we work backwards to see what's needed for fundamental processes. If we start from just fundamental processes, it takes too long. I think the industry can't wait that long. We need to build on the knowledge already in the literature, try not to reinvent wheels. Some of you have seen this before, and climate's very important consideration in any strategy going down. If you ignore the climate, your technology or your discovery can only be good in glasshouse. I can tell you an example which we came across ourselves. We try to understand what will it take to make native plants survive in the lead and zinc tailings. Okay, so in the field, we tried 3 times, they die within 6 months. Whatever we put in, they die. Because the oxidation brings the pH down to pH about 3. And zinc concentration went above 1200 ppm in the pore water. So we took back, students did a trial. We could grow the plants for 2 months, no problem. What we found out now is in the well water condition, it's actually the pyrite doesn't oxidize. So if you do that recommendation to the field operation, it won't work. So you have to be very careful. So really, the expected technology transfer and delivery to the real-world problem is certainly cost-effective. Money is not a limitation. Everyone can do it. Second thing is, this is very important for scientists to consider. It has to be adaptive to operational capability, because we should not expect in the future whoever is going to implement the technology have PhD degrees. We should benchmark on farming operation or conventional mining operation. So we have a lot of capability to implement that. Because at the end of the day, we do research, we want to deliver a solution and solve the problem. And another thing is, this one, I don't think many people talked about it, is minimal secondary risk implementation. So you implement this should not create expected secondary. For example, if you propose a technology to treat the tailings or treat the red mud, but you should not generate large volumes of wastewater which you need to manage. Those kind of technology cannot be implemented. And sustainable, so post-established management and maintenance, this is also very important to be considered. Okay? Thank you. So a lot of my effort is focusing on functional soil and soil system, try to make it right so native plants have a chance to establish and evolve. Any questions? Thank you. No? No question? Good. All right, next Anja Urban. She's an environmental specialist from Queensland Aluminium Limited, dealing with a lot of real-world challenges.
Is that just the only change that has occurred? I'm going to take it up, and that is the same order?
David Parry is not here.
Yeah?
Yeah, so I've taken his spot because I've got to catch a flight.
Yeah, and that is the same order.
Yeah. Sorry about that. Yeah, so as Longbin said, I'm from Queensland Alumina. We're in Gladstone in central Queensland. So we're one of the oldest refineries in the world. So we established production in 1967. We had a number of expansions throughout the years, and we were about the world's largest refinery for 40 years. We got overtaken in 2007, and we still produce about 4 million tonnes of alumina per year. So that means that on any given day we produce about 10,000 tonnes of alumina, but also 10,000 tonnes of red mud. So we use the bauxite that mainly comes out of Weipa, and we produce the alumina in Gladstone, and most of our product gets shipped throughout Australia. So just a quick overview of our production process. So we use the Bayer process. It's generally a high temperature, high pressure process, and we use sodium hydroxide to dissolve the alumina out of the bauxite, and out of that process we then get the red mud that we have to deal with eventually. So at our tailings facility, so the red mud gets piped by about 8 kilometres of pipeline down to the red mud dam in a wet slurry. So we use seawater as a transport medium. Back in the day they used fresh water. There was a drought on, we didn't have any fresh water, so what's close to the ocean, we use seawater. As part of that process they worked out that seawater actually neutralises the mud. So a lot of, most refineries in the world don't neutralise their mud. So they found seawater neutralises the mud. There's ample of seawater in Gladstone, so we now have since then improved that process, and we run an excess of seawater to bring the pH down to about 9 from about a pH 14. So we've got our little neutralising facility that was built in 2007, and we operate 2 new red mud dams, and then we had an old red mud dam that sat underneath here, and that was only partially neutralised. So just quickly about the process of what we do. So the red mud gets poured into little holding dams, I guess, within the dam. We let it sit for about 10 to 20 days, wait for a bit of cracking to appear, and then we use the mud farming process to try and get rid of excess water. Throughout this process, so this whole process takes about 40 days. At the end, we end up with a very compacted, very uniform, stable little cell that helps us from a stability perspective, but it also maximises the amount of storage space that we take for our red mud. So by the time we close in probably 2082, our red mud dam facility will close. We will have about 1,200 hectares of red mud to rehabilitate. So worldwide there are obviously a large amount of red mud dams. All of these use different types of methods of disposing of their red mud. So some just dispose it off as a wet slurry, some as a dry filter cake. Most of them are unneutralised. There's only one other saltwater neutralised facility in the world, and that's also in Gladstone, and they only started operating in 2004, so we don't really learn much from them. They usually come to us for learnings. And because of this, and most of these refineries are still operational, there's no successful rehabilitation of a red mud dam facility. So there's a lot of trials going on, but nothing on seawater neutralised red mud, and so we can't really learn from those experiences. So Longbin already talked about the regulatory requirements, that it's got to be safe, it's got to be stable, everything like that. One of the key things around the stability is obviously the geochemical stability of our waste. We can't have a waste that may react sometime in the future and create additional hazards that we might not have foreseen. Although we do find that our mud is very stable, we've got some old deposits, 50 years old, and they haven't changed one bit in that period of time. So you wait and see probably won't work for us. So there are other emerging requirements within our industry, at least from what I've seen, above and beyond what is sort of generally accepted, and that we're starting to see from the regulator that the capping has to be guaranteed for at least 1,000 years post-closure. So I don't think many people talk about that in this space at this point in time. Also, the other thing is the natural landform design. So you have some kilometre-long straight walls, nice little benches, that won't work for the regulator in the future. So we are starting to see and having to amend our design and our dams to start accommodating this. But obviously the rehabilitation has to address some of this as well. They do want to see capillary break layer to reduce salt rise, and then some of the requirements we have on some of our landfills on site is we cannot have any root penetration into the waste material. So for us, what we want to achieve for our site is we want to have minimal quarry resources in our rehabilitation. So that is topsoil, clay, any other sort of fill. That's basically based on, we don't want to create any secondary environmental damage by clearing large scales of native forests to try and get quarry material. There's also a lot of cost around associated with that, but the other thing is availability. So there's no topsoil in Gladstone, and there's very limited clay or any other sort of material there. So the other thing we want to do is we want to minimise the long-term environmental risk. We want to have a self-sustaining native vegetation cover on our red mud dam. We are not going to go for a regional ecosystem or some type of remnant vegetation because we don't think it's achievable. If it is, great, but we don't think we're going to get there with what we have. So native vegetation is sort of minimum for us that we're trying to aim to. And we also need to interrupt the hydraulic connections between the waste and the surface and stop the salts from rolling up. And because there's nothing out there, no one's done this before, there's a significant amount of research that's required to come up with a solution for us in the next 70 years. So some of the factors that we deal with in our, I guess for rehabilitation is obviously climate is a big thing for us. We're subtropical. we're very dry certain times, like we get 3, 4, 5 months without any rain, and then we get some of our, or most of our annual rainfall in 1 or 2 really big events, and those sort of years seem to be increasing rather than reducing. We're a net evaporator like most of Australia is, and we have a very big resource shortage for topsoil, fill and clay. Tailing specific factors for us is a big thing, so because we neutralise with salt water, we're highly saline, above 60,000 microsiemens per centimetre, so even your salt could start struggling with that. We also have a very high chloride-based toxicity, so that some of the other refineries that don't use seawater, they don't have the chloride to worry about, they only have the sodium to worry about. We still have high alkalinity. While we neutralise to pH 9, we get some reversion of some of the sodalites in the mud, and the pH ultimately goes back to about pH 10. The mud is very uniform, so it's clay, it gets compacted to about 10 to the minus 9, and it's got very low nutrients, so it's very hostile to any sort of plant growth. So the research that we're doing, it has to be cost effective. It also has to be take into account long-term material availability. So I don't want to use anything that I won't have in 70 years' time. So for an example, we've just done some trials on our ash dam, which is relatively easy to do, but we found the best thing that works is hoop pine mulch. Add a bit of that. Now everybody in the forestry industry is going out of hoop pine, so no one likes it anymore, so we won't have that available, so now we're going to have to start again and work on something that's available in the long term for us. So the other thing that I think is important is sharing of research outcomes. So it's great to do things behind closed doors, and no, I don't want to share this because I've come up with this great idea, but for us this doesn't really help. And it costs us a lot of money to invest into this research, and I don't really want to spend it if someone else has done this already. So I think it's really, really important that people start sharing things more in this sort of space. And I think the other thing that's important for us is how can things be applied by broad acre scale type farming operations. You know, it's great if things work in the lab, but if I can't apply it out in the field by an operator that hasn't been trained properly, or that might just get a bit of a sheet of instructions, this is what you do, that doesn't really help us. So to try and overcome this gap, we've started a partnership with Longbin's team here, and what we've said is we set aside a 2-hectare area on our red mud dam. So this area will never be used for red mud storage again. It's received probably about 30 years of red mud that sits underneath this area. And we're just going to put a wall across here and start raising our wall across here. So we've closed that area earlier this year, and we've been working very closely with the regulator on telling them what we're doing, but also to bring them along on the journey. Because they've got certain expectations, but they don't know what their expectations are going to be in 70 years' time either. So what we're trying to do is we're trying to educate them and bring them on the journey to try and teach them what is applicable for this type of closure scenario. So what we're doing is, so we had part 1 of our trials was a laboratory trial just to see what could actually be done. So what we're trying to do is bio-neutralise our mud to pH below pH 9. We're doing that by using organic material additions. We're trying to dissolve the alkaline materials and remove the salts we've imitated rainfall, but that's and just accelerated that cycle. We're trying to improve the physical structure in the red mud, so ultimately the goal is to try and use the red mud to grow things. Currently we can't. You won't get anything to grow. So we're then also trying to get an acceptable root zone, and so the abundant organic the locally abundant material for us is what we're using is urban green waste, so that's waste that's collected by the local council, people's leaves, trees, weeds, whatever they get, they mulch it, we take it. The other resource that we have available is treated effluent, so our council does not have a licence to discharge their treated effluent. We use that as wash water through our process. So we know that at closure we will most likely still have the entire town of Gladstone plus the surrounding communities of treated effluent available. So we can actually work with irrigation. And then the other thing we're using is we're trialling different mineral amendments. So the pilot study so far has shown that by adding that green waste and some of these other materials, we can actually get sort of relatively sustainably to a pH of 8. We've also worked out by running some rainfall simulation tests that you can reduce the salt content to below 10 millisiemens. So we might be able to grow some salt-tolerant species, pioneer plants in there. So the pilot study that we did in the lab, or that Longbin did, was actually quite successful. So we've managed to get some germination happening, and we actually had proper, so that's salt bush, and we had, I don't know, 120 days you grew them? 125 days, so they grew actually quite successfully. We're excited every time I got a photo of the plant. So what you can see in the untreated mud, there's nothing happening, and we also ran some DNA trial tests. So the amended mud has actually started getting some microbial addition, so that's natural, so we didn't inoculate this. So part 2 will now look at how can we scale up what we've done in the lab into the field. So we've got our local farming contractor who's spreading seeds and mixing things without actually really amending his machinery. So we will just explore whether the methods of what we've done in the lab, how we can scale that up. So it's quite promising, but there's still a fair bit of work. So what we're looking at is initially just growing pioneer species, so we're working on a 3-year basis, and from there on we'll see what happens if we can grow saltbush successfully. And we will also work out how we can best monitor this in the field in the long term. So what we've got to work out is we've got 2 hectares here that are quite easy to do, but if you're talking 1,200 hectares, that's got to work out how much money that's going to cost us. So we're relatively early, so what we're doing, this is just sort of just summarises what we're looking at, is you've got your initiation phase, so that's really just making the chemical properties of the mud okay for anything to grow. And then we're trying to, as part of our research at the moment, getting into the sort of this primitive soil-like material that can sort of grow some pioneer species, and later on down the track hopefully we'll get into this where we might actually start growing some sort of mixed vegetation that can sort of self-sustain. So next steps for us is quite excited, we're just finally there with spreading most of our materials. So that's the other issue that we, for example, encounter is availability of local contractors to actually do the work for you. So just because you want it done, it doesn't mean it gets done in the time. There's always pressure on resources, so hopefully by September, October we will have everything set up in the field. We'll look at the whether the most effective treatments in the lab are also the most effective treatments in the field under our current climate conditions. Looking at the physical structure development of the soil, looking at the colonisation with soil microbes and establishment of the pioneer species. There is also other work in process. What we're looking at is what you can do, whether you can engineer some sort of capillary break layer instead of using conventional clay. So, because that's obviously quite expensive, try and source clay and put a conventional capillary break layer in. And as far as what we've heard from the regulator is this is an absolute must. They will, at this point in time, not move away from that. Anyway, thank you very much.
I noticed that the 2 hectares have 2 different colors of there. One is yellow ash and another one is red. Is that another treatment there?
It is another treatment. It's probably not very scientific treatment. So basically we've got a separate, so we use coal-fired boilers for our energy and for our steam generation on site. So we have a large ash dam on site. That ash dam runs out of capacity in 2035, so we will be transporting ash down to the Red Mud Dam. So we know that ash is we can very easily rehabilitate ash and actually get plants to grow in it. So what we're just doing is we're actually putting various depths of ash over the red mud and just see whether that works into the long term. We're not applying any capillary break, but this is really just one of our operators at the red mud dam had an idea, and we thought, oh well, why not throw that in there and see what happens.
You said that it's not going to be sort of a true rehabilitation or restoration space, but you're going to target growing native species on there. Do you have any restrictions in regards to where those native species can come from in terms of a problem boundary or?
I don't think so much for where we are, because we are isolated. So the red mud dam's isolated on an island to start off with. So we would be looking at species that won't take over native vegetation in the surrounding landscape. I'd say we will look at weed potential for those species, but personally I don't have any problem with taking plants out of WA if we find they can grow in our red mud. Right.
If the trial with the organic works, where will you source the organic stock to take the cost into play?
Yeah, so look, that is something we are looking at. Ultimately, if it is successful, we will start looking at getting into contracts with the local council in terms of materials. I mean, it is. I don't think you will have. We won't be able to stockpile enough until closure, because we just don't have the space available, so we can't start doing that now, but there is things we're going to have to look into, especially closer to closure that we get. But yeah, I'm pretty sure that by the time closure comes around, Gladstone will certainly still be there, and it is actually quite a steady waste stream that they have.
I think another thing, if you identify how much you need, what type you need, you can always identify degraded land around the town, so you can stock green biomass, just hire chipping people chip. So it becomes sustainable.
Yeah, we have actually looked at getting into just approaching the council to just take the green waste directly from town rather than going straight to landfill. We've sort of discarded that at the moment because of the risk of secondary materials entering that waste stream, such as asbestos and things like that. So, but that is something we're looking at as well. Yeah, look, we do have a fair few weeds. We don't have a lot of the really nasty weeds, but yeah, that's certainly something we will potentially look at, because it's the same sort of material. You know, throw it with a red mud, I'm sure it'll go.
One more question.
Just something about mineralogy research has sort of line, particularly in
So, technically, yes, we are doing actually some work with a different group within UQ here at the moment, doing some trials on top of the roofs in column tests, and they actually show some promising results that the salts won't actually rise, but the risk is always there. So unless we can prove that in the field that they don't, we assume that they will. No, because then you won't have neutralised mud, and that has a whole different environmental risk to it, and we don't have any ability to process the leachate out of that mud then at that point in time.
Okay. All right. Last night, sure.
I just wondered if you had any thoughts about doing alternative land use, because if it's going to be a long-term venture to put salt bush back in this area, that doesn't seem to me to be a particularly useful or valuable outcome.
The salt bush is there, just the interim species, pioneer species, to catalyze the whole soil development. They are not the ultimate vegetation goal.
Yeah, so we have had a look at, so we've had a very extensive workshop last year as part of our revised closure plan into other options that are out there. We don't feel they are viable. The only thing that we do think might be viable is high value real estate, because we are talking a 55-metre high mountain. You know, ocean views without the tsunami risk. But that is, at this point in time, that is not something that we can sort of bank our hopes on and that we would get approved. So we're looking at just what are the options, what can we actually feasibly do. Like if we find that we can't get anything to grow, we will look at maybe pursuing other land use options.
All right. Okay.
Have you proposed it? You said, oh, we can't get that approved, but you haven't proposed.
Well, you can't propose that right now because the regulator won't agree on any post land use options until you're actually about 5 years from closure. So and currently within the housing market in Gladstone, I don't think you will be building anything. But yeah, no, we've put it up as an option. But that's discussions to be had later. But you don't want to be 5 years out from closure without an alternate plan.
Okay, all right. That is not the end of the next speaker. Thank you. Our next speaker is Ping Lu, who is is environmental superintendent or manager of ERA. And Ping come from the ecophysiology background. He's very dedicated to this project with ERA. Have been quite fundamental and instrumental to this trial. And so he'll tell us what's the journey and headache he had so far.
Okay. Thank you, Longbin. Basically, I would like to present the result of so-called long-term observations of our trial landform. Basically, what will be the future of our Ranger mine. It's a collaboration work with Longbin here and also a few colleagues at the University of Charles Darwin. And also the work is it's based on many of my previous colleagues' studies as well, so it's acknowledged. How it works for moving? Yes, so first I would like to acknowledge our traditional owner of our site is Mura people, and that was there on Trial Landform last year. Quickly, where is Ranger uranium mine? It's actually we are in the close to Darwin and in the Kakadu National Park somewhere here. The ranges belong to the Energy Resources of Australia's company named ERA, and we actually produce about 1% of the world's electricity supply. That corresponds about 90% of Australian power use, electricity use. So we are currently actually in the phase of closure. So we're doing planning and also implementing the closure activities. So we're concentrated on the revegetation activity we're doing. So the requirement, we call it the Ranger authorization, have environmental requirement, is basically to revegetate the distal side of Ranger project area using local native species, which is similar in density and abundance. So yes, you have heard yesterday and today many talks around that by the supervising scientists, the research institute. So it's about, in total, about 1,000 hectares of land need to be rehabilitated. That including 700 hectares of wasterock covered area and also 300 hectares of the impacted. Basically, it has been irrigated with the effluent. The natural woodland. So I focus now today on the wasterock covered surface. The challenge we have with the wasterock covered surface for revegetation is we have a very strong seasonality, basically 6 months without rainfall, and also very high annual variability in rainfalls. It basically means that we can have consecutively 2 years without much rainfall. And we have extreme events, so the cyclones is affected Darwin very often. And another one is the physical and biological environment for the final landform is a very hostile growth medium. Basically, it's a substrate of wasterock only. We don't have laterite, weather rock, or we don't have soil, topsoil, whatever. So also we have very high fire and wind pressure in the surrounding Kakadu National Park. In 2008, we have established we call it Trial Landform, which is basically to demonstrate that ERA have the capability to rehabilitate the future Ranger uranium mine site, and we tried direct seeding versus tubestock. And we tried also the importance of mixing some laterite into the wasterock. That's actually, this option is no longer available for the final landform construction. And also the importance of irrigation, because we will have no choice of revegetate only during the wet season. We need to revegetate actually across all year round during dry season. The trial landform is about 8 hectares. And we have different sections. The wasterock only, we use tubestocks, and the wasterock with direct seeding. And then another 2 options is actually mixing some laterite into it. As I said, this is no longer an option for us. So our features will be just the wasterock only. That was 2008, and then March of 2009 we started planting. That's already started dry, the weather, and so we need irrigation coming. And we have introduced the first control fire in 2016. That's 7 years after the planting. That's the wasterock just at the time of planting. So it's still got some fines there, but they are not soil, even weather rock. So it's just crashed due to the heavy machinery working around. So that's 1 year after the planting. You can't see anything basically. It's not green at all. A little bit of greening here. That's the tubestock have been planted. So basically tubestock here, the wasterock only, and then tubestock on the wasterock mixing with laterite. And in the middle are direct seeding. That's 6 years after. It's lots much better now. So you have the wasterock only, tubestock trees, and then the wasterock with direct seeding, but because it's not, direct seeding was not very successful, so actually we have infill planted with tube stocks, so that you see some trees there. I will concentrate mainly on these 2 plots, mainly this one, we call it Trial Landform 1A section, is the wasterock with the tube stocks. So you can see this caravan as a scale, the tree is quite large now. And then next to it, despite we have infill planted, those trees you see is basically was the infill planted tube stocks, and the original direct seeded trees are very small still. So that it's not really ideal, especially when you have the high pressure of weeds around it. So it actually opens the space for the future weeds invasion. In terms of the effect of irrigation, certainly irrigation have a very, very positive impact on the survival and also the species compositions we achieved. Without irrigation, we have a significantly less surviving, and especially the species composition has been heavily skewed to few species like acacias, grevilleas. Those can survive without irrigation, even during dry season. So it's not really an option for us. And we do have a significant difference in surviving between species for the tube stocks we have planted. Certainly, some like Eucalyptus tectifica is actually almost 100% of success survival rate. And the tintinans, Acacia mimula, and Ratis, and Acacia laticens, that's quite good. They are the top survival ones. Tube stock, after the infill planting in 2010, we actually have around 1,200 stems per hectare, and that you can see progressively reduced to 2014 around 900, close to 1,000. I think it's 900 some stems. That's the original tube stocks, but in 2016 when we do the surveys, including the original tube stocks plus the natural recruit, it's almost 3,000 stems now we have per hectare, so it's quite a lot. It's too dense. Direct seeding, that's the only thing I probably talk about direct seeded area, is actually originally you have 2,000, talking about wasterock only, so about 2,000 individuals has been germinated, and then very quickly retracted to the around 600 maybe by 2014. As I said, only a few species was actually survived. The growth, so the tree, you can see that that's the wasterock only substrate. They actually have very positive, very strong growth of the time. So now by the end of 2015, you will have the average trees of 5.5 meter tall. And also they have more than 25 species has flowered and fruited. I should say we have planted about 40 species trees and shrubs on the trial landform just to find out whether they can perform or whether they can grow on the wasterock landform. And many actually started to have natural regenerations from their own seeds. That's natural regeneration from seeds, from their own seeds. The tree flowered fruit and then regenerated. Some typical example is the Corymbia setosa, the flowered fruit, and then new young plants grow from seeds. And also green plants, that's which very important bush tucker, and you can see and fruits heavily and the seeds seeded on the ground, and then you see many of these younger seedlings come up, and still survive even nowadays today. And you see some indicators of natural the nutrients cycling. For example, you see all the mushrooms come up, and fauna colonization starts as well. You have rats, rock rats, and that's basically happening within actually 2 years' time of the landform construction. And then later on, you will see more. It's like the partridge pigeon, which is actually a protected species, and the family here actually nest on the trial landform. 1, 2, 3 is a family, and we see the nest of there. And the legless lizards and wallabies, dingoes, it's all present. It's captured actually photo by the camera, the motion camera. And just one day, that's where actually the trial landform, the sections have never been irrigated, and we planted, and certainly later on we infill planted trees. That's myself, and that's the tree height. That tree is actually flowering the time in 2016, and that day I have heaps of birds there. Just one day you captured so many of birds at that site. And we have also tested whether our trees will be fire resilient, yes. And we have prescribed fire burns in May, that's the dry season, beginning of dry season in 2016. On the lateral side, because lateral side got some weeds there. As I said, we were not talking about future to using that lateral mix into the wasterock, but at least to give us some ideas about the species, whether they are resilient. So it's about 95% of trees survived after 3 months of burn. That's the next wet season, or the section has been burned. Okay, so now it's probably talking about more science now. Fortunately, I have only got 3 minutes left. Can the vegetation be self-sustainable over the time? the question asked is that because we have very different soil profile, that the west rock spool is just no structure, it's just west rock, and that's after five years, and then you have the 1,000 years of landform comparing the analog side. Can we grow the same vegetation on top of these two? So we know that in the top end that the soil water availability is actually the one determinant of success of our vegetation, because they have six months of wet season, whether you can survive or not. And basically, we actually try to answer the questions whether we have enough plant available water. So the first things we know what the natural environment does, vegetation does. So we assess what is the analog or reference site water use, and then we assess whether the substrate have enough water, and then we compare them. That's the analog site. It's in the nearby areas. And we measure the subflow in the vegetation, and then that's basically the sediment changes of the water use of the vegetation. Basically, this transpiration. And we installed on the trial landform. We installed the moisture probes into different depths. So the west rock we have actually, you have about 25% of voids because it's quite a coarse material, and that voids is actually some is air, some will be water. And the particle size distribution is basically we have more than 60% of rock only, and then the rest is actually the fines, less than 2 millimeters. So we have a lot of sands, quite significant actually, more than it's about 15% of silt. That's actually best material for the water holding. And then we have very, very minimum clay. So we use USDA, SPAW soil water calculators to calculate the plant available water, 2 parameters. One is the fuel capacity, and then another one is the permanent wilting points. Then we work out whether the 4 meter deep of west rock landform will have enough water. So basically, we find that we have 400 millimeters of plant available water potentially in the system. That corresponds about 10% of the total volume. And then you compare the water needs with the PIW of the landform using the CSR Weaves model. We're very close to the end. So I passed already. And so basically, we're using worst case scenario is basically we have using a site on top of the hill over the pit, and that's have deep west rock structure. We compared the two, and then basically we did the simulations of the dry season plant available water over 117 years. Then we find that for all the years, basically, we have a positive surplus of the water in the system. Another question is, the same question is whether we have enough water. Then we said yes, we have enough water for 4 meters, but just considering the variabilities or uncertainties, we must say, okay, maybe 7 meters is a better value. So 4 to 7 meters should have enough water for vegetation. Another project, very quickly, 2 minutes here, is whether they have enough nutrients for the vegetation, and whether the nutrient cycling is happening. So we have in collaboration with Longbin's group here. Just a quick thing is actually 2010 we have compared these two sites, analog site and trial landform. By then the pH of the analog site was 6.3, and the trial landform was 8. And then this year we have found that actually the pH is closer. The trial landform one is actually moving closer to the analog site. And in terms of total nitrogen, it's actually when we started the the total nitrogen levels is 10 times less than the analog side, but now you will see that's had been significantly increased, and that's it's just more than 1/3 of the current analog side. So from a nitrogen very, very poor situations to now, you see some nitrogen has been accumulated in the system. And we have many other results, but here we just capture probably the most important things is that during the wet season, you can see the microbial carbon. This is actually the trial landform ones. The carbon is less than the analog side, but the basal respirations is indicating how hard the microbial is working. You can see that actually the trial landform, they are working very hard, but their productivity, the mineralization rate is very low. So the soil microbes are working very hard, but it doesn't produce much. Why? Because it's under stress. What is the stress? Basically, it's because I don't have a ground cover layer yet, so the ground surface is exposed, and then the temperature is high and it's dry, so the vegetation even during the soil microbe, even during the wet season, is not as efficient as required. So we actually now is try to establish understory. So we have an understory. Now our focus is mainly on the deep-rooted legumes and other perennial grasses. Some pictures have some success, especially with those treatment with direct seeded into the litters area. So that means we need fines, we need litters, so the understory can grow. Thank you. I take my time.
We can have a couple of small questions. Just move on. One question. No? Okay. All right. Thanks. Thank you. We have our last speaker, Dr. J. Stevens from King's Park. I will introduce anymore because he just gave a talk this morning, earlier this afternoon. You can take these. I will.
Okay, thank you very much. Today I'm here to talk about a collaborative partnership between Kings Park Science and Sinosteel Midwest Corporation. I'm getting a sense that this is probably one of the more easier programs of the 3 or 4 that we've heard today. There's a few acknowledgements I'd like to make, and that's all the people that did the on-ground work from Kings Park, but also 3 other people. Kingsley Dixon, who helped myself in managing this program, but also 2 people from Sinosteel Midwest Corporation, Wayne Enner and Stuart Griffiths. And the reason why I guess I need to acknowledge Stuart Griffiths as the General Manager of Operations is he's pretty much kept us on our toes on this whole journey because of the requirement of getting the science in a directly applicable way for what these guys want to try and achieve on their mine site. For Sinosteel, it's a state-owned enterprise out of China, so Stuart is always having to argue the case for restoration at this site into the Chinese companies. And if you don't have that communication into the executive teams, then things can fall over pretty quickly. I'm just going to focus on a few plan establishment considerations that we encountered on the journey. So Sinosteel came to Kings Park about 8 years ago now, and they came to us pretty much around compliance issues. The EPA in Western Australia had highlighted that rehabilitation wasn't working quite so well, and that in fact it probably wasn't even a strategy that could really be considered as a mitigating option for reducing the proposal impact. So the EPA, in the face of the fact that rehab wasn't working, over time have just increased the level of compliance, which I think is absolutely fantastic insofar as the science supports. That's the problem, I guess, that we have. So some companies are being hit with high targets, 70% targets within short time frames, 5 years of completion, and now we're talking about moving into self-sustaining. I've heard that in a few presentations already this morning, and that's where the regulators are really focused at the moment. I'm not quite sure what self-sustaining actually means, other than we can begin to have a conversation with companies and the regulators about what self-sustaining actually means. So Sinosteel operates predominantly out of the Midwest in Western Australia. A couple of active deposits in Coolanooka and Blue Hills, and future deposits. So for a Chinese-owned company to step into the Midwest of Western Australia, they clearly don't understand the system quite as well as some of us may, or at least think that we do. So they came along to Kings Park to get some science input into how they can handle their rehabilitation. And as I said, the regulators were pretty hot to trot with these guys, because they had a pretty high target of 70% composition to be achieved within 5 years of the cessation of mining. For Sinosteel, there was extra complexities. They were working in a threatened ecological community on banded iron formations. So banded iron formations, pretty much a pure iron ore, not a lot of topsoil sitting over the top of them, and they have pretty well intrinsically linked ecological communities that sit on top of those pure iron ore ridges. The other thing that was a little bit challenging for the operators were where the actual mine was and where they were going to be required to rehabilitate was already in disturbed areas. So we have intact threatened ecological community here, we have somewhat of an intact system here. This has all been pre-mined and pre-grazed. In fact, some of the first iron ore out of Western Australia came from this site back in the 1960s through Western mining. But the site I want to talk about today is a small impact zone here, which is operating within the intact threatened ecological community. As part of that impact, they were required to offset an area of the same size over here. So the company perceived quite a few challenges, as you would. A couple of the major ones were the relinquishment and tenure associated with their obligations in the future, and they wanted to really reduce liabilities to ensure compliance was met. Everyone had an understanding that there wasn't a lot known about BIF systems generally, and there was a really challenging environment to work across. The bottom right picture there is a waste rock dump from the 1960s, and you can see what happens when you don't quite get your rehab right or undertaking rehabilitation at all. But also, the bottom left picture is some of the pit voids that they were just left with as part of their of what they inherited, really. But it gives you a sense of what the landscape really looks like. It's pretty much pure rock with a skeletal topsoil sitting over the top. So because they were on a really short time frame of 5 years, I approached Kings Park, and there's a really nice paper by Ben Miller and the rest of the guys at Kings Park here outlining a scientific framework and the types of questions that you need to be able to consider or address when you're looking to try and achieve some of the targets that the regulators are now setting. In this paper, there's 5 themes that pretty much step through everything from targets and planning to resilience, and a lot of questions that underpin those things. In the 5-year journey that we had with Sinosteel, I've just highlighted some of the red boxes there, some of the things that we had a look at pretty much. So you can step through these things pretty quickly when you know what kind of questions you want to ask and which ones are the highest priority questions to really address. So in terms of achieving a 70% target, well, actually that was pretty I won't say straightforward, but we actually were able to achieve that for that small site. I won't go into details on the breakdown of the species, other than to say there's still a little bit of work to do with some of the common and the uncommon species. But if you step back and just use some of the scientific principles and resource it effectively, and I heard Longbin say that before, if you put money into it, you should really just sit back and see what you can achieve. And in some of these sites where people didn't think it was possible to achieve a 70% target in a short time frame, well, we're actually starting to say, well, you know, maybe we can. So maybe that's what we should be looking at. Maybe there are opportunities for restoration in some of these environments. But what I want to talk a little bit about today is just 3 of the innovations that we looked at through the journey, parking the compliance to one side. The first thing, and we've heard this already, is around topsoil deficits. When we first met with the company, the first thing we did was have a look at all of their matrices that they had available to them. So that was topsoil, all of their waste materials, seeds and so forth. And what we're able to do is then just do some back-of-the-envelope calculations to see, well, clearly we don't have enough topsoil to be able to restore your whole site. How much waste material do we have? How can we blend it effectively? And then is that going to be cost effective for you guys to be able to do on site? And as I said, as soon as you can start talking in terms of costs and benefits into a company, they get engaged pretty quickly. And what we're able to show was that we can actually dilute topsoil down, 25 to even maybe a bit higher, to cover greater areas without compromising seedling emergence. And we were diluting with waste materials that was actually crushed rock down to 5 centimetres, and that's something we hadn't really considered previously. We were just thinking about waste as a general waste rock matrix, but Sonostill said that if just give us the dimensions of the rock that you need and we'll be able to crush it down to whatever you want. So an engineering solution that had come from the company that we then had to factor into our thinking, because we didn't think that anything like this was possible. But for them, it was all about the cost versus the benefit. If they could suck up a little bit of the cost in extra crushing, they can provide it into their rehab, which would offset the cost in terms of the overall restoration. So yeah, what we're able to show, these just from 6 species, really basic data, just in terms of emergence and early settling survival. If we had topsoil, we get around 15%, so nothing flash, granted, but we can actually blend it up with some material from the waste and we don't get any significant detrimental impact on emergence. It doesn't work for everything. There are other waste materials, and waste rock on itself was no good to actually support just the early stages of survival. So again, it's just understanding the system that you've got to deal with and what are some of the wastes that these guys are going to encounter to see which ones may be beneficial and which ones aren't going to be. Now, that was just a really simple trial, but clearly there's a whole lot of laboratory but also field-based studies that underpin how we get to a 25% or 30% dilution of the topsoil. It's understanding the intact system as best we can, particularly the surface structures and hydrologies that are supporting the germination and early seedling establishment phases, but also understanding things like the future risk of erosion and runoff when you start mucking around with the cover designs. So the next thing that we really wanted to get our head around, I've heard the irrigation being touted in a couple of previous presentations, was what actually happens in terms of climate interactions when you're trying to hit a restoration target within 5 years. So what we wanted to understand was, well, how does actual natural rainfall affect seedling emergence? Are we going to see emergence every year, or just when the rainfall's at its highest? And then how can that inform maybe future irrigation strategies when we're looking to achieve some restoration targets? So this was before the massive infrastructure development up in the Pilbara, but it was an idea of Kingsley's actually to construct a rain-out shelter where we could simulate various rainfall regimes, looking at average, above average or the 80th percentile, and ambient conditions. And what we're able to show is that, well, no real surprises, but in some years, so there is an ambient plot somewhere down here for most of them, but basically what we're able to show is that you can't expect any kind of survival when you're relying on ambient conditions, at least regularly. You are going to have to put water into the system to begin to increase the seedling, even just emergence. We're talking about average or above average conditions just to get to 5 or 6% out of the ground. So if these guys are trying to achieve a target within 5 years and the rainfall is that sporadic that we're actually looking at 1 in 10 year kind of events here to really start kick-starting the system. So this was really useful for not only the company to see what might be achievable, but also for the regulator. So this information then feeds back to the regulators to say, well, actually some of these targets that you're setting may not necessarily be applicable when you're talking about some of these systems, because we're not going to get that regularity of inputs over the timeframes that you're talking about. And the last thing I just wanted to touch on was, well, where to from here? And this was moving a little bit beyond compliance for the company, but it was trying to understand, once you had the system ticking over and plants maturing and the system kind of settling down, how can we understand if it is going to be resilient or somewhat resilient or self-sustaining going into the future? And we only use 2 parameters for this. One is plant physiology, how plants function in their natural system, and kind of soil water contents. And we used a process of electrical resistivity tomography to really understand that. We compared these blue dots, which were the reference systems with the rehabilitated systems, and just looked at how the plants, which were these dots here, were performing when they were, and also how the substrate was functioning hydrologically. I've just got a couple of graphs to step through here with a couple of different species. On the y-axis we have water potential or level of stress, so the greater the number down here, the more stressed the plants are as we step through time from September to May. We have a reference system which is blue and a rehabilitated system which is an orange. So basically what we're able to show, these are 2 or 3 year old plants in the rehab system compared to mature specimens in the reference, and that's always a point that we have to think about, is we don't actually have a true reference system in some of these sites. We're always comparing a maturing system with an already mature state. And what we're able to show is in the rehabilitated systems throughout the year, these plants are ticking along pretty well. They're not stressed at all. The reference system, plants go into periods of stress and then they come out of it, and that's just the natural way of functioning. So that was for one species. For another species, Acacia ramulosa, again we have the same kind of story. Rehabilitated sites are ticking along pretty well, so plenty of water. These guys aren't too stressed at all. In one reference system, the blue dots were coming down here and then we tick back up over here. But in another reference system, we have a completely different switch, and that was because there was rainfall events at this reference site compared to this other one. So it's even just understanding the reference site and how water relations may be impacted by these sporadic rainfall events, which really can throw out your understanding of how well the system is actually ticking over. Other species behave very differently. This is Melaleuca. It was pretty much unstressed in both the reference and the rehabilitated states. So overall, if we look at how the system is coping with or is resilient to a rehabilitated site compared to a reference system, well actually if you look at plant water status, you'd probably say things are doing okay. But this is the initial point through time, and we understand that the system is going to develop in terms of density, and as the systems mature, the whole system is going to shift. So this is a first point in time. But as I said, we measured plant performance compared to reference and rehabilitated soil profiles. And pretty much these figures are self-explanatory. We have either 20 or 50 metre long transects across the surface, and we're having a look at about 10 metres of profile in a reference system compared to about 5 in a rehabilitated system. The reason why we're looking at 5 metre profiles here was that the roots we thought didn't really go below 5 metres. We're only talking about 2 or 3 year old plants. In the reference system, we had no idea where the roots were. These things are growing in pure rock. So this was really a test of method to see if we could get some meaningful data out of measuring pure iron ore and in the rehabilitated sites. And what we're able to show is that this is a change through time. So again, self-explanatory. If it's green, it means that the system hasn't really changed through time. And this was a comparison between, I think it was July and September in one year, so it'd been naturally drying out. So green means that it wasn't drying out at all. If you had blue areas, it means it was getting wetter. And if you have red areas, it was either a void or things were drying out at the surface. And what we're able to show is that the rehabilitated sites, as you can remember, the plants are doing okay, but you can see there's a lot of competition near the surface here for the water resources, as opposed to, we see a little bit of that in the reference system, but their roots are going to be down in and amongst all of this other stuff here, so they're probably going to be not really competing for water quite so much. So this is our first insight into how the systems are starting to rebuild and repackage themselves. So just to conclude with, in terms of outcomes, this project has at least demonstrated that some of the conditions that are being set by the regulators may actually be achievable if you put a little bit of research and a little bit of funding towards them. But some of them may not necessarily be quite so straightforward. So if you think about the 5-year timeframes, possibly some of those things need to have a little bit more science basis to underpin some of those statements. All of this work's been published and it's online on Sinosteel Midwest Corporation's webpage, so if you want to have a look at the full extent of all of the research that was done there, by all means do so. This guide was put out so other people that operate in banded iron formations around Western Australia, Australia or the world can have a look at what's been achieved so far. There's been some training, some publications, but as I said, this is really only the early stages of some of these understandings. And the ARC Centre for Mine Site Restoration is really picking this up from here on in and is going to progress that further. So in terms of the seed work, Adam Cross is going to be leading future developments in seed enhancements and seed dormancy. Sean Tomlinson is looking more at the rare species component. So sitting on some of these ridges, there's a couple of rare plants. And then we have some ecophysiology postdocs or PhDs that are sitting in that space as well. So I'll leave it there. Happy to take questions. Yeah, there's a whole lot of different criteria out there. Functional groups would be a good way to look at the system, absolutely. The diversity of plants that we got back here, we made sure that those plants reflected the functional groups that occurred in that system. So we knew that we wanted to get the tree canopy, the shrubs, the herbaceous layer back, and that's where we had some of those different targets. And we also wanted to make sure that the common, uncommon plant species that mapped to those functional groups were represented. And that's why, even though I say it's 80%, in some of those functional groups we were probably a little bit under. So yeah, no, that's a good point. Peter. That guy there. Yep. Yeah, no, these guys wouldn't have set this. This was a conversation with science informing the regulator decision. But yeah, you're right, some of that terminology is coming in. The problem is it comes in and then goes out with the next condition, and getting a little bit more consistency and understanding the trends that the regulators are thinking of is important. But you're clearly needing the science to help guide some of those conversations. I'm quite supportive of the regulators setting quite high targets and making companies try and stretch for it a little more.
I have one question. Where does the 5 year coming from? Why 5 years? Do you think we can achieve in 5 years' time?
Again, regulatory decision. As I said, we can understand some processes in that time frame, but how other processes mature.
5 years? Scientists or government?
That's come from a regulator. I'm not aware of any of the conversations around that.
The regulator is asking at the moment to do a review of the history of changing condition setting within the WA.
Yep.
And through the science groups that we've got involved, trying to actually provide some recommendations for what we could improve some of that condition setting.
5 years in that kind of setting, I think, could. Even Alcoa's gone down to the south, there's a bauxite mining area. I don't think even that kind of environment can promise 5 years.
I guess also the life of mine here is quite quick. So those guys were in and out in 1 year as well. So I guess if you put timelines that are too long into the future, I guess you want to make sure that they're going to be able to deliver something pretty quickly to limit your risk going forward.
The regulator only sets the conditions if the mine triggers the EV Act. They otherwise self-regulate their own conditions. So these conditions were only set because there's an EV Act related issue. G from floor, something like that.
Last question?
So how did you go about setting your targets? So you've got a species list. Presumably there was surveys.
Yeah.
Were there species densities or percentage cover on those species that sort of quantitate or detailed data that came from those surveys that got you the granularity of setting your targets for
Yeah,
density of different species?
yeah, this was a really interesting case in that the condition, and I was going to go into a lot of this detail, but in 15 minutes you can't. No, it's a great question because this specific condition referred to two surveys that were undertaken, one of which had a number that was down here and one had a number up here. Literally 50 versus 250 species. So the company goes, well, what's our target? What do we actually have to aim for? So then we had to unpack all of the survey work that had been done at various scales and various different methodologies and pretty much have a go at doing it ourselves so we could get that information that we thought was required, again, in the hope that that kind of survey effort in the future would be undertaken by the company at the right scale to collect the right information to address these conditions. So there was an absence of information there to inform the companies. We tried that, and then we ended up having to do it ourselves at the scale that was appropriate.
All right. Thank you, Jason.
Thanks very much.
And, also, let's thank all the speakers this afternoon for the whole session. So if no any burning questions, I think we finish here. Don't have beer.